Welcome to The Explainer. Today, we're literally putting on our hard hats and looking at math through the eyes of a master builder. We're breaking down a really fascinating chapter titled A Tale of Three Intersecting Lines. Think of this as your ultimate, hands-on construction manual for the absolute most basic closed shape in existence. We're going to uncover those hidden geometric rules that completely dictate how our physical world fits together. So, grab your blueprints and let's get building.
All right, let's dive right into this. Here is our structural blueprint for today's explainer. First, we'll examine the basic anatomy of our shape. Second, we're upgrading our tools to build with actual precision. Third, we'll uncover the triangle inequality rule, which is basically the physical law of what can and cannot connect. Fourth, the 180-degree magic. And finally, we'll wrap up with altitudes and some very special structural variations. Let's get to it.
Section 1. Anatomy of a triangle. The basic raw materials.
Now, at its core, a triangle is beautifully, elegantly simple. It's the most basic closed shape you can possibly make. It consists of exactly three corner points. We call those vertices. Connecting these pairs of vertices are three straight line segments, the sides. And exactly where those three sides meet at the corners, well, they give rise to three internal angles. That's it. Vertices, sides, angles. But from these simple raw materials, some absolutely incredible structural complexity arises.
Section 2. Building with precision. Tools for the job.
So look at the stark difference here between just guessing and truly engineering a shape. The source material points out something really interesting. If you want to build, say, an equilateral triangle where every single side is exactly 4 centimeters, using just a ruler, it's incredibly frustrating. You draw the 4-centimeter base, and then you just kind of guess the angle for the next side, right? Hoping that remaining gap magically equals 4 centimeters due. It's just slow, repeated trial and error. But when we pair that ruler with a compass, game changer. We upgrade from blind luck to highly efficient, guaranteed precision.
And here is the exact procedure to pull that off without any guessing. Step 1, draw your baseline using the ruler. Step 2, open your compass to the exact length you need, stick the needle on one end of your base, and sweep a nice, long arc. Every single point on that arc is perfectly that distance away. Step 3, do the exact same thing from the other side. And right where those two sweeping arcs perfectly intersect, boom! You've pinpointed the exact, undisputed location of your third vertex. No guessing required. Connect the dots, and your shape is flawlessly constructed.
Section 3. The triangle inequality rule. The physical laws.
Now, I really want you to think about this for a second. If I walked into a hardware store and handed you any 3 random pieces of wood, could you always connect them end to end to form a closed triangle? We usually just assume 3 lines automatically equal a triangle, right? But nature actually has a very strict building code. And the data from our source text brilliantly illustrates the drama of construction here. Look at these lengths. Sets like 3, 4, and 6, or 5, 5, and 8. Total successes. They lock together perfectly. But look at those impossible fails. If you take lengths of 2, 2, and 5, what actually happens? Well, you lay down the 5-unit base, you attach the 2 2-unit sides to the ends, you fold them inward to meet, but 2 plus 2 is only 4. They physically cannot bridge that 5-unit gap. They'll literally just dangle there, mathematically refusing to connect. Same exact thing goes for 10, 20, and 35. 10 and 20 only reach 30, there's no way they'll ever span a base of 35.
So the crucial takeaway here is this universal law, the triangle inequality rule. For any triangle to physically exist in our world, each length absolutely must be smaller than the sum of the other 2 lengths. If even one side is longer than the other 2 combined, the bridge collapses. The gap just cannot be closed. It's basically the ultimate test of our building materials before we ever even strike an arc with our compass.
Section 4. The 180-degree magic. Internal structural law.
Okay, so how do we know what the internal angles of a triangle are going to add up to? The source text highlights this brilliant piece of historical engineering. Back around 300 BCE, the Greek mathematician Euclid documented a truly ingenious idea in his famous book, The Elements. By simply drawing a straight parallel line right across the very top vertex of a triangle, the relationship between those inside angles suddenly just clicks. It becomes obvious. They perfectly unfold to form a straight line right against that parallel beam.
And a straight line, as we know, is exactly 180 degrees. This is known as the angle sum property, and it is a massive, totally inescapable result. Honestly, whether you draw a triangle the size of a tiny postage stamp or a massive triangle stretching from the Earth to the Moon and over to Mars, if you measure those 3 inside angles, they will absolutely always total exactly 180 degrees. It's just a fundamental law of flat geometry.
Section 5. Altitudes and special triangles. Building walls. Now let's see how a specialized tool builds a perfectly straight wall, which in math we call an altitude. An altitude is just a perpendicular line dropped straight down from a top vertex to the base. Now trying to do this with just a ruler, usually pretty sloppy. But, as the source diagrams clearly show, if you align your ruler firmly to the base and then place a right-angled set square right on top of it, you can smoothly slide that set square along the ruler. And the moment the vertical edge hits your top vertex, you draw your line. It drops at a perfect, absolutely uncompromising 90-degree angle.
And this leads us to a really fascinating structural variation. What if the shape itself is already perfectly straight up? In a right-angled triangle, one of the interior angles is exactly 90 degrees. So, in this unique little building, you don't even need to drop a new line through the middle to find the altitude. One of the actual outer walls, one of the sides itself, functions as the altitude. It's essentially its own perfect support pillar.
All right, so we've covered the complete structural blueprint today, from the raw anatomy to precise compass arcs, the strict laws of inequality, and that wild 180-degree rule. So I want to leave you with a direct challenge from the source chapter just to test everything you've learned. Ponder this. Is it actually possible to construct an equilateral triangle, meaning a triangle where all sides and all angles are perfectly equal, that is also a right-angle triangle? I want you to think about our 180-degree magic rule and what 3 equal 90-degree angles would add up to. I'll let you do the math on that one. Thanks so much for joining me on this explainer, and keep building your knowledge.